all of 3 classes left. For good or for bad, that's where we're at. What's really crazy, just to kind of, make things even seem even tighter. So here's today, and there's our final. It's 2 weeks from this Thursday. And that will ultimately be the last graded assignment in the class. So I sent out an announcement today. There is no recitations next week. This is the last week of recitations. This week is the last week of recitations. So everything's finishing off. So this week you'll be done with recitations. You won't have to show up for those anymore. The quiz, the last quiz. So I guess you all have a quiz that's due tomorrow. No, you don't. You don't. You do not have a quiz yet. I'm so used to them being here every Wednesday. You all will have a quiz that will open. You all will have a quiz that will open this Friday on rotation. This Friday there will be a quiz that opens on rotation, and that will not be due until I double check Tuesday or Wednesday before the final. I think I might have made it Tuesday just to give people time. Let's see. I don't trust that window, so I don't want to open it. So yeah. Anyway, there's one last quiz, and there's the final, and then, that's it. So, today and Thursday are the last days I'm teaching you all new things, and then this coming Tuesday, a week from today, will be the review. The review, I will be going through kind of a quick summary of everything we've done. That'll take me like 20 minutes or something, 20, 30. I'm not going to spend that much time on the test one review, test two review, but just like I'll quickly run through those to remind you all of things I already taught you. Then I'll make a test three review, which actually might already exist on there. And then we'll solve some problems. And hopefully at this point, you feel very comfortable with the things that were on test 1 and test 2, and so you'll just need to spend your time kind of reminding yourself of it. The beautiful thing with Physics 1 is all the concepts kind of pop up here and there. You don't have to be done using them. We'll still use velocity. We'll still use acceleration. So kinematics kind of hasn't left our brain, hopefully too much. But anyway. All right. Last class. Let's do a recap. What did I teach you all last class? I taught you that every single linear variable, every transverse variable has a rotational equivalent. So instead of x, it's theta. Instead of v, it's that w omega term. Instead of a, it's alpha. And every single equation I taught you up to this point, basically, if those variables exist in it, we can swap over the rotational variables and make a new equation. And so we did that with the kinematics equations. Yeah. Yeah, the P is momentum, so there's a regular momentum, and then unfortunately we're not going to have the time, there's an angular momentum. But it's the exact same way that you all do regular momentum, is how you do angular momentum, just with the swap term. So sadly, I would normally cover that, but hurricanes, right? So there is the last, I can open this up. So the problem set exists. And I can finally tell you all what you need to know in the problem set, and it's actually most of it, which is nice. I'm kind of happy about that. I will be able to cover like everything up until number 9, 10, 11, and 12 or angular momentum. I will not have time for those. So they will still exist here. If you want to learn them on your own, go for it. But just for your all's knowledge, everything in problem set 3 is kosher. Except for 9, 10, 11, 12. They're good problems. There's nothing wrong with them. We just don't have time for me to teach it to you, so I'm not going to test you on it. Okay? Because we lost some time, I'm not able to cover angular momentum. It is a really cool concept. It would be great if I could cover it, but you'll be all right. We're going to cover enough that you'll have the skills to learn it on your own if you need to in the future. Okay, so great. We got all our equivalents. We got all these things, and so I introduced the variables. So we talked through each of these, what they were, and then where am I trying to scroll to? Okay, remind you all that every kinematic equation you had has a rotational equivalent. Everywhere there's x, replace with theta. Everywhere that there's v, replace with omega. Everywhere there's a, replace with alpha, and they work the same. They work the exact same. Building on this, we also have the relationships between. So if you want to go to x, if you want to get kind of how far you're going to travel, remember it was just r times theta. If you want to get v, if you want to figure out your linear velocity, it's just r times omega. If you want to get the acceleration in terms of the angular acceleration, so to go from angular to linear, you just multiply by r. Really nice, really straightforward. Yeah. R is the radius, yes. And this is specifically assuming no slipping for some of this kind of stuff. Little kind of small detail in there. If something's rolling. If you're going to use these equations and it's something rolling, it has to be not slipping. That's kind of in the background. But yeah, nice. Good stuff. So, we also practiced, where is it at? We practiced the direction of these because they are vectors. And the direction, you got to do this whole right-hand rule thing. So this is a really good one to just practice. Make sure you remember how to get the answers out of the page. Make sure you remember how to do it. Try it out yourself before I say anything. Don't worry, I'll show you, but try it in your own brain. And by brain, you got to use your hand. Remember, it's the right-hand rule, so take your hand. Make your fingers curl in the direction and it's rotating, and your thumb points in the direction of angular velocity. It is called the right-hand rule. The right-hand rule. Use your left hand, wrong answer. If you use your left hand, it's the wrong answer. And that's one of those, it will happen to you. Because if you're a right-handed person, you'll be doing the test, and you'll be bubbling things in with your right hand, and then you'll use your left hand to get the wrong answer. Yeah. Yeah. So in general, I'll give you the picture, and so then you just make your hand match the picture. So like in this case, I curl my fingers this way, my thumb points.
How do I know it's not curling my fingers this way?
So you need your fingers to curl along this. If I do my thumb this way, I can't. My fingers can't do that.
Will there be any way that we could do this?
No. Yeah. The only way your fingers, you basically want your fingers to match the.
Wasn't there a right hand rule where then thumb was pointing up or down or no?
No, not for any of these, no.
Okay.
Yeah, it's pretty much almost exclusively out of the page into the page, is drawing it otherwise in page. But if this was like flat on the page, or like if it was in plane and it was going like this, then it'd be up, but that's really hard for me to draw for you all. Yeah, it's a great question. And then, let's see if I can erase this quick enough. All right, that wasn't quick enough. All right, maybe you didn't catch it. Try this one out. I'm not going to give you the answer, Here, we'll just open it up. Why not, right? I'll give you all like 30 seconds, 40 seconds. See if you all remember how to get angular acceleration, which is good review. So a piece of gum, slowing down. All right, 20 more seconds. Oh, I'm glad I asked this. All right, 5, 4. Yeah, that's fine. I'll wait a couple more seconds. So remember, y'all, the right-hand rule does not tell you the direction of acceleration, of angular acceleration. The right-hand rule tells you the direction of the angular velocity. The right-hand rule only tells you the direction of angular velocity. So you got to do one more step. You got to do one more step. All right, so 3, 2, 1. So in this problem, angular velocity is into the page. Great, but I'm not asking about angular velocity. We need that though. Angular velocity is into the page. I'm slowing down. If angular velocity is into the page, how do I make that arrow smaller to slow it down? I point it out of the page. If omega is into page and I'm slowing down, then alpha is out of page. So there you go. But yeah. Which makes me worried. I'm like double checking my answers. I'm like, I'm pretty confident in this. Yeah. So, right-hand rule only tells you the direction of angular velocity. If you're slowing down, it needs to be the opposite of that. So, be careful, y'all. Remember, acceleration, the sign of acceleration, if I tell you I have a positive acceleration, that does not mean speeding up. If I tell you a negative acceleration, it does not mean slowing down. Acceleration is always relative to velocity. A negative acceleration is speeding up if you're moving to the left. A negative acceleration is slowing down if you're moving to the right. So the same logic you all use for this, for linear motion, you apply to this. If I'm slowing down, if my angular velocity is into the page and I'm slowing down, then my angular acceleration is opposite that. If you're slowing down, they're opposites. If they're speeding up, they're the same direction. All right, cool. So then, what was the other thing I reminded you all of? I reminded you that if you're going in a circle, so we started this problem, and it had a bunch of steps. So we had a wheel rotating, and I said, what is the magnitude of the acceleration vector? And I told you all this is a really good problem, because basically, you can do this problem so many ways. And it's a nice connection between angular variables and linear variables. I give you angular variables as like givens. You can convert them. But you also have to remember that if something is speeding up, if something's spinning faster and faster, it has a centripetal acceleration, but also the tangential acceleration is also existing. And so anyway, we got both terms. Centripetal acceleration is v squared over r. Tangential acceleration, there's two ways to get this. This is one of them. Just find the final velocity, find the initial velocity, plus at. You can find a from that if you know the final. And that's one way. Anyway, so I jumped to this slide where I got more work shown. But another way you all can solve this problem is you can do it all in terms of angular variables. You can do everything here in terms of angular variables. So you can turn this a net equals, so it's v squared over r squared plus, oh, I put that in the wrong spot. So you got the tangential. So remember, y'all, I'll just put it here just so we can see it. So v squared over r squared. You can rewrite this entire equation in terms of rotational variables. So the other way you all can do this is a tangential is just going to be alpha times r. Remember, if you go from linear to rotational, just multiply by r. Super nice, super easy. So that's one. And then the other thing you can do is you can change this v to omega r. And then you can divide that by r. And that's another way you all can solve this. And you can do it all in terms of rotational variables. And for the sake of time, I sadly won't do that, but you can try it for yourself. Calculating angular acceleration, really simple. How do you calculate angular acceleration? The same way you all calculated regular acceleration. Remember, omega final equals omega initial plus alpha t. It's the exact same equation. This equation here and this equation up there in the top right are the same equation, just one's linear, one's rotational, and it works. So if you know the final omega, which we do somewhere, there it is, 2 pi f, 6 pi. And we know the initial, which is 0, and we know the time, which is 5 seconds. You can find alpha. If you find alpha, how do I find... Let's see, what color do I want to do for this? Blue sounds nice. If I want to find this omega final, I'm just omega final. It's the exact same equation. But in this case, t will equal 0.5, I believe. That's when we're calculating things. And this t will equal 5 seconds. Really, really, really good problem for you all to do, because I'm not so much worried about this net acceleration thing. That's like, sure, that's a thing that you do. What I am worried about is, do you know the connections between linear and rotational variables? Can you go back and forth between them by multiplying by r and things like that? So that's why I really, really like this problem, because you get to do it a lot, and there's multiple ways to do it. So try it out for yourself. It's a good one to kind of work through. Once you kind of see how to do it, it's not that bad. This looks like a hot mess because, again, I write a lot more and I've shown multiple ways of doing it. And so it looks all kind of crazy. But when you do it for yourself, it's not a long problem. The math is not that hard. It's just, do you know the relationships between those variables? And are you okay with kinematics? All right. So I'm going to skip this one. Don't have time for it, but have fun. So let's get into torque finally. If I have a bolt and a nut that's stuck together, should you use a long wrench, a short wrench, or it doesn't matter? I'm trying to draw a nut in case you haven't seen that before. I don't know. It's really hard to draw. If you're not sure what this is, Google it. All right, 10 more seconds. Either of you've used kind of wrenches before or you haven't. That's kind of this problem. 5, 4, 3, 2, 1. So this problem can be reset. When you push a door, what's easier to open? If I push it really far away from the hinge or really close to the hinge, it's the exact same thing. If you have something that's really long, you can twist things easier. That's maybe the best way to phrase this without using vocab. If you have if you have a long lever, it's really easy to lift something. You know, there's this saying, if I had what's that thing called? A lever the size of the universe, I can lift planets or something like that. But you've experienced this with doors. When you open a door, where do you push on a door? As far away from the hinge as possible, because it's easier. Yeah. Yeah. Yep. Torque and moment of inertia are the last two things I need to teach you all. So, anywho, a long wrench. If you ever experienced this, you'll find out for yourself. Long wrench. It's the best. But why? Because there is something called torque. So, remember, I always want to connect the things that you all have learned and previously to the things that you're learning now. So there's F equals ma. If you apply a force, it causes things to accelerate. If you apply a force, it causes things to accelerate. The analogy here, if you apply a torque, it also causes things to accelerate. Just instead of normal acceleration, it's rotational acceleration. And then instead of mass, and this is what I hope to be able to get to today a little bit as well, moment of inertia is how mass is distributed. We're going to learn today. For now, don't stress it too much. What I need you to know is if you apply torque, things accelerate rotationally. If you apply a force, things accelerate. And so to that end, the more torque you apply, the higher the rotational acceleration. That's going to be a theme. That's going to be a really common theme that's going to be coming up for the first half of today. So here's torque. Torque is R cross F. You know, it's kind of like what I've been saying. How do you go from a linear variable to rotational? Multiply it by R. And it also kind of follows that relationship, which is nice. I kind of just realized that today. There is a sine theta as well. These are vectors. So we can't just multiply them. We have to do a cross product or a dot product. In this case, it's a cross product. And the reason? will make sense. I'll explain it in a second, but for now, kind of jot it down. The symbol for torque is lowercase tau, this little t thing here. So it's just like a little tail with it's like a T with a little tail on it, or like a backwards J, I guess, but it's lowercase. Tau. Greek letter, I don't know where it is in the Greek alphabet, but it's somewhere in there. The units for torque, really, really, really easy to remember. In fact, I don't actually have them memorized. I have no idea what the units for torque are off the top of my head. But I do know torque is R cross F. What's the unit for R? Meter. What's the unit for F? Newtons. We did it. It's Newton meters. It's literally just multiplying the units for R and F together. And that's the units for torque. How nice is that? Super simple. Yeah. Newton meters. It's a good point. It does end up being the same. It's the same unit as work. Yeah, it's interesting. Never kind of realized that. Yeah, it does end up being the same unit as work, which does that mean something? I don't know. I don't think so. Nothing comes to mind off the top of my head, but that is a really good connection I hadn't thought about before. All right, let's close all that. Always the notifications. All right, so I have taught you all dot product before, which actually was what was mentioned. If y'all remember, work was the dot product of force and distance. And remember, a dot product was the magnitude of F times the magnitude, it's the magnitude of the two vectors times cosine. That was a dot product. If you have a dot product, that was the case. And I'm just going to replace these with two random variables. So let's say C equals A dot B, just to show you all that it's general. These are vectors. When you do a dot product, it turns into a scalar. Now, a cross product is it's another way of multiplying vectors. It's still A times B, but instead of being cosine, it's sine. And what I really hope, so look, you all will take Calc 3 at some point, and they'll do dot products and cross products. You'll do a bunch of math, and my experience with that is I had no idea why I was doing what I was doing. A dot product multiplies the parts of vectors that line up with each other. So remember, I drew this picture forever ago. If you have A and you have B and you have some angle between them, if you multiply A times cosine, you get the part of A that's parallel. So a dot product is just multiplying the parts of vectors that line up with each other. That was work. Find the parts that are parallel to each other. What is a cross product? Instead of multiplying the parts that are parallel to each other, do the other thing. What's the other thing? Well, there's parallel and then there's perpendicular. So by multiplying A times sine of theta. The cross product is literally just multiplying the parts of vectors that are perpendicular to each other. Two ways to multiply vectors. Either multiply the parts that line up with each other or multiply the parts that are perpendicular to each other. That's what the cross product and dot product is doing. And physically, hopefully this will make sense. So I'm going to use this ridiculous whiteboard thing as an example. Because it's the best thing I got, and it does the job. If I want this thing to rotate about the right side of this whiteboard, if I push forwards, it doesn't rotate. If I pull outwards, it doesn't rotate. If I make my force and my R line up with each other, it doesn't rotate. So we don't want the parallel part. How do I make this whiteboard spin in place? If the R vector points, so R points away from the axis. R always points away from the axis. If I want this thing to rotate, I either push forwards on it or backwards on it. I.e., I push perpendicular to R. If you want something to rotate, anything you want to rotate, if I want to rotate this desk, I don't push into the desk, I don't pull out of the desk, I push perpendicular to the way I want it to rotate. Alright, so, here's a wall, or here's my axis, here's my object. How do I get that thing to spin about the axis? Pushing this way, useless. Pushing inwards, useless. It ain't going to rotate. Makes sense. How do you get it to rotate? And just to show you all here, R always points away from the axis of rotation to wherever you are. So how do you make this thing rotate? You push perpendicular to it. Either of these are going to make it rotate. You've experienced that. When you want to open a door, you don't try to push the door left and right. You push it perpendicular to away from the axis of rotation. So that's what we do that's why we do a cross product, y'all. That's all that's happening here. You don't need to know the reason why, but if you understand the reason why, it will make every single rotating thing make more sense. It'll make using this math make way more sense. There's a reason behind the math. That's the reason. Great. Okay. We have to find the direction of torque. Great news. It's actually very simple. I have a recipe of how to do it here, and in teaching it this last week, I realized there's a really easy way to do it. Remember I told you all foreshadowing. I haven't taught you this, but one day I will, as in hopefully tomorrow, Thursday. Torque equals I alpha. The direction of torque is in the direction of angular acceleration. Great. Okay, so what? All right, 3 scenarios. We're going to practice these 3 scenarios, and I'm going to teach you how to do it 2 ways. One is a right-hand rule. It's a different right-hand rule. It's slightly different. And the other is using the right-hand rule we learned before. The easy way to do this. Which way is this thing going to accelerate? Which way is this thing going to accelerate? That's all you have to ask yourself. If I push this thing up and to the left, is it going to accelerate counterclockwise or is it going to accelerate clockwise? That's the question for you. Hopefully it's going to be fairly obvious. It's going to accelerate counterclockwise. Like push a wheel and that's the way it's going to rotate. So how do you figure out the direction of torque? Just curl your fingers and it points in the direction. Same old rule that we just used. Super, super easy way of doing this. If you can figure out which way it's going to accelerate, you can figure out which way the torque is. And how do you figure out which way it accelerates? Just look at the direction of force and you know it's going to spin that way. You all have spun a bunch of things, seen a bunch of things spin in your life. So that's the easy way. That's one way of doing it. Just figure out which way it's going to rotate. So it's angular acceleration. Alpha is going to be out, so therefore the torque is out. Fantastic. The other way I call the swinging door method. No one calls it that, but I think it's easy to remember. Point your fingers in the direction of R. So this is this right-hand rule that I'm mentioning here. I call it the swinging door as of 2 days ago. Point your fingers in the direction of R. Pretend like R is a door, and I want to swing it towards F. So if I point my fingers in the direction of R, I need to swing it towards F. There's literally only one way to turn your hand where I can swing this, and it's the exact same thing we just did before. And you get that your thumb is out of the page. So, how do I get F to swing towards F or towards R? How do I get R to swing towards F? That's how. Okay? And this is true of any cross product you ever do. If you ever take the cross product of 2 variables, you point your fingers in the direction. So we're doing torque equals R cross F. You point your fingers in the direction of the first one. You swing it towards the second one, your thumb points in the direction of the vector. That's always going to be true. You'll see that in Calc 3. All right. So this one, torque, out of page. You all do the next one. In fact, do the next 2 if you can. Find the direction of torque in the next 2 examples that are on the board. Yeah.
Does it matter which hand it is?
It does. If you use the wrong hand, you get the wrong answer. Case in point, if I rotate both my hands the same way, just test it for yourself. Your thumbs point in opposite directions. So, good question. All right. So again, 2 ways to do it. One way is to put my fingers in the direction of R, and then make it so you can swing R in the direction of F. Look, if I point my fingers this way, I cannot swing my fingers I can't swing them all the way to F. That doesn't work. I can't. It's not happening, y'all. I can't make my fingers go inside my hand. So I do it the other way, and now look, I can make my R point in the direction of F, and my thumb is into the page. There you go. So I can take this R and I can kind of swing it so that my fingers point in the direction of F. Great. One way to do it. And then the other way that I realized a few days ago, much easier. Which way is this thing going to rotate? Which way is this thing going to accelerate? Is a better way of phrasing that. It's going to accelerate that way. Boom, we get the same exact answer that way. Just use the original right hand. So this one is torque into page. And the last one, I'll give you all the answer to that one in a second, but I want you to try it for yourself. Actually get some responses and see if this is making sense to y'all. You got a 50-50 shot. I know there's 4 answers here, but 2 of them are silly. So I got a circle, there's a force being applied at the bottom of that circle. The axis is dead center. I didn't specify it, but you could probably assume that. That's the axis of rotation. If you're like, there's no R vectors, draw one. Draw the R vector. All right, 10 more seconds. And 5, 4, 3, 2, 1. Kaplawi. All right, so there's no R vector drawn here. Whatever are we going to do? We're going to draw it ourselves. R vector points away from the axis to the point you care about. So I put my fingers in the direction of F, and there is literally only one way to put my hand so that my fingers can actually curve towards F. That's the only way. Good luck. Try it another way and see if you can make you cannot curve, do not swing your fingers backwards. It's bad. Don't do that. Close your hands, like you're doing a weird wave. All right. Great. So this is going to swing this way, or remember the other way you can think about this. It's going to experience. I really, really, really want to clarify this. I am not drawing the direction of that it's rotating. This is not the direction it's rotating. Case in point, just because you're applying a force down here doesn't mean this thing's rotating counterclockwise. Really easy example. This wheel is rotating the other way. Let's have it rotating clockwise. Just because you apply a force here doesn't mean it magically comes to a stop instantaneously. This could be like a braking force. This could be like the calipers on your car, your braking calipers are slowing it down. The force does not tell you the direction of motion. The force does not tell you the direction of motion. It tells you the direction of acceleration. And acceleration is not always the same direction as velocity. I really, really, really want to make sure that's clear because that's such a common mistake. People are like, oh, it's getting pushed to the right, so it's moving to the right. You don't know, you don't know that for sure. Anywho, that's the direction that it's angular accelerating, and so therefore, out of the page. Great. So this one is going to do the opposite. It's going to have an angular acceleration into page. Let me double, triple check that before. Yep. And alpha is into page, therefore torque is into page. And I'm even going to put this here, direction of omega, no idea. Did not give you enough information for you to determine which way it's rotating. No idea. It's like me saying to you all, I push a box to the right, which way is it moving? No idea. There's no way you can figure that out. Just because I'm pushing it to the right does not mean it's moving to the right. There could be something else pushing it. All right, cool. Torque, all right. So like I mentioned, why do we care about torque? The same reason you care about force. Torque in and of itself is useless for you unless you know the moment of inertia. Just like force. I can tell you I push an object with 1,000,000 newtons. So what? It tells you absolutely nothing. I push an object with 1,000,000 newtons. What's it going to do? I have no idea. If I push the earth with 1,000,000 newtons, nothing is going to happen. I might push some dirt downwards. Whereas if I push this pin with 1,000,000 newtons, it's gone. We don't actually care about the force value. We care about the acceleration. Anytime you all calculate force, it's to find acceleration. Anytime you all calculate torque, it's to find angular acceleration. That's really important to keep in mind. All right. So, hey, how do we figure this? Look, it's that guy again. F equals ma. He also came up with torque equals I alpha. And next week's lesson means this week's lesson. Woo! So, let's practice torque. A horizontal beam of 3 meters and mass 2 kilograms and then mass 1 kilogram and width 0.2 meters sitting at the end of the beam. There's a nice picture of it. What is the torque of the system about the support at the wall? So we're trying to find the torque, and our axis of rotation here is going to be the wall. That's what it's going to rotate about. So, I'm going to jump straight to step 3. We're actually going to kind of work our way backwards. It says torque. So, we're going to use the torque equation. Magnitude of R times the magnitude of F times sine of theta. And the reason we're doing this, because this is the first time we've seen this problem, is this equation is going to help us determine what the heck we need to even figure out from this picture. Because it's not going to be obvious what our givens are going to be. Well, by looking at this equation, it's going to be obvious. We need R and F. Like, to find torque, you need R and you need F. But if you don't know that equation, that kind of might not be obvious. Now, I'm going to give you all a hint. There's 2 things generating a torque on this object. There's 2 forces generating a torque. I'll give you all a few seconds to see if you can figure it out in this picture. What 2 things are causing there to be a torque? Spend some time. Think about it. I'm going to make this picture really big because we're going to need a bigger picture we're going to draw on this some. Why is there a torque at all? All right, so, really just the question is, what forces are acting on this? What do y'all think? What forces are making this thing want to rotate? Yeah. There's force due to gravity. And then, once you realize it's a force due to gravity, what's experiencing gravity? The beam and this box. They're both experiencing a force due to gravity. Now, here's the thing. Every single piece of this object is experiencing a force due to gravity. But man, that would be a pain to break it into an infinitely small amount of objects and do that. If only we had a handy way to pretend like the object was located at a single dot. We can do the center of mass of each object. That's the benefit of center of mass, y'all. That's the reason we covered it. Center of mass lets us take this beam and pretend like it's at a single spot. Go ahead and decide where that spot is for the beam in the box. Decide that on the picture in your head, and then I'll show you, and we'll see if they match. Where is the center of mass of the beam? Where is the center of mass of the block? Center of mass of the beam? Shock and awe, it's at the center of it. It's a nice symmetrical object. Center of mass of the block? Dead center of that block. Fantastic. Nice and easy. So, gravity is going to affect the beam, and gravity is going to affect the block. So we can find those. F1 equals M1 times G. F2 equals M2 times G. Nice and straightforward. So that's going to give us our forces. Force due to gravity. The next question is, what is the R? There is an R. Where is that force 1 located? Where is that force 2 located with respect to the axis of rotation? How far away from the axis of rotation is it? I'm going to give you all 30 seconds for this, and I'm even going to tell you that the vast majority of people are going to get R2 incorrect. All right, so R1 is fairly straightforward. It's dead center of the beam. Where is that located? 1.5 meters. R2 is also straightforward. And the answer to that one's going to be 2.9 meters. And then immediately, you're going to start to realize why. Once the answer's kind of there, So this is R1. R2 is over here. It's at the center of the block. The block is not sitting, the center of the block is not at the very right end. It is very tiny bit to the left of that. The block is 0.2 meters wide. So if this entire distance is 3 meters, this little tiny gap here, that's 0.1 meter because the block is 0.2 meters wide, and you got to account for that. This is the beauty of a picture, y'all. The picture lets us see that easily without that picture. And this is where, in this case, it's really important where things are sitting. And it might seem like a tiny difference, but if I made this block at the end 10 kilograms, it would drastically change the answer. You can do the math and prove that for yourself. I don't know how much it changes things here. So torque equals question mark, just to fill this out. Now, the last thing we have to consider, this is like when you did forces. When you add forces, you have to consider direction. When you add forces, you have to consider direction. If I have a force to the right and a force to the left, I don't just add them. The force to the right is positive, the force to the left is negative. You have to account for direction. If things are fighting each other, they're not adding just normal. You got to subtract one. So to that end, these are just adding. They're helping each other. They're not fighting each other. That's the easiest way to kind of realize that. Both of these are causing it to want to rotate in a clockwise direction. You can decide whether or not you want that to be positive or negative. I really don't care, as long as you know they're the same direction. Great. So we get torque equals R1 times F1 plus R2 times F2. And you may ask yourself, what happened to the sine of the angle? It's a good question, and it's one that's important to ask. The angle between R and F and the angle between R and F are both 90. In both cases, you do need to consider that. That is important because it can affect things. Case in point, I have a problem on the quiz where it's not 90. So be ready for that. I think I have it on the quiz. Either I did or used to. I don't know. If I hold something up at an angle, so basically I'll just tell you all there's a quiz problem that's either on it or used to be. I don't know, but I'll mention it just in case it is on there. I hold something up at an angle. When I hold something up at an angle, if we draw that situation, so I got, here's my arm. There's my axis. There's the force of gravity. My R points this way. My angle here is not 90. You have to find the part of FG that you just have to multiply by the sine of that angle. All right, so be ready for that. They're not always perpendicular, y'all. Just because it's ideal to push things perpendicular doesn't mean that's how that always works out. The real world isn't nice. Things are messy. Okay, so step 4, easy peasy, just plug things in. R1 is 1.5. And then F1 was the mass, which is 2 times 9.8 plus, that's not going to fit nicely. Oh, that's so sad. All right. I'll move it on to a new thing. I just don't have room. Classic. Once you have all the givens, you don't really need the picture. You don't need the words. You got everything you need. All right. Plus the mass of object 2 is 1 kilogram times where it's located is 2.9. I'll put these in the right order. 2.9 times its mass times 9.8. And that comes out to 50 something. I don't have that memorized. I just solved it this morning, so I remember it was 50 something. Maybe 58 or something. I don't remember. I'm going to plug it in. 1.5 times 2 times 9.8 plus 2.9 times 1 times 9.8. Oh, I was so close. 57.82. What are the units for torque? Super easy. It's the unit for distance times the unit for force. Comes from the math. If you do not put the 2.9 in there, you get an answer of 58.8, which is one off. May not seem like a big deal, but it'd be very easy for me to make a problem where it did make a big difference. There you go. Nice, straightforward torque problem. And again, what's the point of finding torque? Does absolutely nothing for you. So the benefit here is engineering application-wise, you will have things that are designed to withstand a certain amount of force or a certain amount of torque. So by knowing the torque, you can actually determine if certain devices will break or not. That is kind of like, there is functional applications to this number. Different systems have different torques based on the materials and stuff like that. When you all are, if you're ever doing stuff with there's like, I forget what they're called, like torque wrenches or something like that. There's ones that actually tell you how much torque you're applying. And there's certain things when you're building them, they give you specifications. Tighten this bolt with 30 Newton meters of torque. And the reason for that is, it's usually freedom units instead, which is awful. But that's to make certain that the nut is tightened the right amount. You don't want to over-tighten something because then it can strip the stuff. And you don't want to under-tighten something because you don't want it to fall off. If you've ever done an oil change, you've experienced when they over-tighten the oil nut. It's awful. So anywho, connections. Torque. It shows up. Anything that rotates, you care about torque. So, onwards and upwards. For me to talk more about torque, though, we get to learn about moment of inertia. Moment of inertia is it's like the only new thing I'm teaching you all. Moment of inertia, there is a calculation for it. It's new. We're going to learn about it. It's going to be great. So much fun. Everything else has a really simple connection to what you've already learned. So, we're going to talk about moment of inertia and how to calculate it. Fun fact, there's integrals involved. Also, fun fact, you're not going to have to actually do any integrals with it because they require generally multi-integral, triple integrals or double integrals, which you're blessed that you haven't taken Calc 3 maybe, so I can't require it of you. Anyway, moment of inertia, we're going to figure out how to calculate it. The derivation for it is so easy. Like deriving it is so simple. We'll see in a second. We're also going to find the rotational kinetic energy. We are not going to define angular momentum, so sad. So really, we're just going to do these first two bullet points. We're also going to calculate rotational kinetic energy. So these ones down here, blame the hurricane. The hurricane's still learning from you. But really, these last bullet points are really, you all could learn that on your own. If everything else here makes sense, angular momentum is really simple. If you're good with regular momentum, it's just more of that. Okay. Why do we care about this? I'm not going to start this problem yet because I'm not going to be super mean. I will give you all what you need to know to answer this. I roll 4 objects down a ramp. A sphere, a hollow cylinder, a solid cylinder, and a hoop. They all have the same radius, and they all have the exact same mass, and they're all released from the same height. Which will reach the ground first, and one of these will. The answer is not all of them. And so the key to this, the key that I'm going to teach you all that you need to know, is that it's hard to move things that are far away from the axis of rotation. It is harder to move things that are farther from the axis of rotation. That's the key that you need to know. The farther a mass is from the axis of rotation, the harder it is to move, and it's really, really easy to explain that. If I rotate my arm, the part near my shoulder doesn't have to move that far. Like, look at the distance it travels. It's really small. Whereas my fist has to travel a huge distance comparatively. You got to spend more effort to move things farther away because they literally have to travel a farther distance. Great. Try it out. Using that logic of the farther away it is, the harder it is to rotate. What's the right answer? Solid sphere, hollow cylinder, solid cylinder. All right, 20 more seconds. In 5, 4, 3, 2, 1. So it all boils down to which of these has the mass closest to the center? Which of these has the mass closest to the... And when I say the center, the axis of rotation. So you got a sphere. There's a sphere in all its three-dimensional glory. Here's a hollow cylinder. Here's a solid cylinder. And there's my hoop. In all its... Well, let's just make it look like that. Fun fact, a hollow cylinder and a hoop, if that hollow cylinder has infinitely thin, if the thickness of their walls are identical, these actually are the equal difficulty. The hollow cylinder and the hoop, if their wall thickness is the same, exact same difficulty because their mass is really far. The hollow cylinder and the hoop have their mass kind of as far away from the center as it can, all on the outside. That makes it hard to accelerate it. That's not necessarily a bad thing. Sometimes you don't want things to accelerate super quickly. And that's always a good engineering consideration. There's not such thing as like good or bad when it comes to materials or when it comes to designs. It all comes down to what is appropriate for the application that you're designing for. So if you want something to not rotate super quickly, these are the ones you want to go for. Yeah. Oh, yeah. So a hollow cylinder we consider like the middle hollowed out all the way through. So like a PVC pipe. Yeah, that's a good point. If it did have the caps, it would be, I guess, a bit better than the hoop in some level. But it's still the worst. That's still the hollow cylinder and the hoop are the worst. Solid cylinder is a bit better because we get some mass located kind of near the middle. So we get some mass that's like all over the place. So that's a little better. But the winner is the sphere. And the reason the sphere is the winner is because it kind of like bulges out. So some of the mass kind of there's some mass it has more mass closer to the axis of rotation. A sphere has more mass closer to the axis of rotation. Yeah. That's a great point. If there is no friction, they all reach the bottom at the same. Yep. If there's no friction, they all just slide down the hill and who cares? But the reason we like things rolling is they work with friction. What's really cool about this problem is I don't care what the friction is. The friction could be like insanely high as long as they all roll without slipping. This will be true. Rolling things are nice because as long as they don't slip, friction doesn't affect them at all. As long as things don't slip, friction has zero effect on a rolling object. That's why rolling things are nice. That's why the wheel was such a great invention. Big fans of the wheel. All right, so this is the key phrase. This is what if you understand this concept, moment of inertia will be fine. Okay, harder is to rotate when things are far away. Great. Torque, great. Slower, all right, great. So all these things, stuff already said. Let's derive moment of inertia. And as always, we start with something that you understand. Kinetic energy is 1/2 mv squared, where v is the tangential velocity. Nothing surprising there, hopefully. Hopefully that's not surprising. Remember that v equals r times omega. Nice, easy connection. So just chuck that where the v is. R omega squared, nice and straightforward. Then go ahead and square it. Nothing crazy there. R squared is r squared. Omega squared is omega squared. Nothing crazy. And then, but what if I have more than one object? What if I have like a bunch of masses at different radiuses? Well, I got to sum them all up. If I got multiple objects, I want to find their kinetic energy. I just sum up that term. And then we just put parentheses around this term. And remember we say for every translational variable, there's a linear equivalent. So we look at our original. Remember that the kinetic energy you all are hopefully cool with is 1/2 mv squared. Remember, v is like omega. 1/2 is like 1/2. And m is like this thing. So let's call this thing a name. It's moment of inertia. Moment of inertia is just mr squared. So it is the sum of mr squared. And the reality is objects that we work with aren't just, technically they're like a bajillion protons and neutrons. And if you really wanted to, you could find their location and add them all up, and that sounds awful. But how do you sum up an infinite number of small things? We have an object, we break it into infinitely small things, make m dm. dm is literally just a mass that's infinitely small. And you integrate to add that up. All an integral is an infinite sum of infinitely small things. So we find out where an infinitely small mass is, that's r, and we multiply it by that squared, and there you go. That is the integral to find moment of inertia. Now, you all are largely spared from doing this integral, because the reality is to calculate this for various objects, you need a double or a triple integral. They're not too terrible to do, but you haven't learned them, so you're spared. I will do this for a thin rod, because that's a one-dimensional integral, and we can do that, and that'll be great. But that's a future thing. That's not a today thing. For now, I just want you all to be okay with that moment of inertia. The farther away you are from the axis of rotation, the harder it is to spin. R squared. You see that term there? And then, there you go. And the units for this. How do I find the units for moment of inertia? Really, really easy. The unit for m, kilograms. Units for r, meters. And it's squared. There's the units. Nice and simple. You don't need to have that memorized. The equation is on the formula sheet. Just as long as you know kilograms is mass and m is for distance, you're good to go. Okay. So let's just apply this to a very, very simple problem. Really, really straightforward. 5 kilogram ball is attached to an end of a 2-meter string. If I spin this ball in the circle, what is the moment of inertia of the system? Assume the string is massless, because if it wasn't, that'd be just awful. And assume the ball is a point mass. So, you got your massless string as they exist. And you got your ball, which is a point mass. And just calculate moment of inertia for a single object spinning about an axis. All right, we'll go for like 40 more seconds. Just remind you all, there's the equation that just showed up before. You only got one object, so you're not summing up anything, but that's just the general. All right, close this out in 5. Yeah. Oh gosh, if you had to worry about the string, you'd also have to you'd have to integrate over the string to find its moment of inertia. The string itself would have its own eye. And then you would add that to this one. Yeah. All right, we'll close this out in 5, 4, 3, 2, 1. And it really wouldn't be the worst thing in the world if I gave you the equation for the moment of inertia for a thin rod. A taut string is just a thin rod. All right, so really straightforward, y'all. There's literally just one object, so it's just mr squared. So it's just 5 times 2 squared equals 20. Yeah, scared you, right? Kilograms times meters squared. Boom. Great. Okay. Now, reminder to you all. I'm not going to actually have you do there's like one problem I have on the problem set for doing an integral for this. just to give you some foreshadowing of it. So we're going to integrate, and we're going to use the same trick we did with center of mass, where we use density. Remember that we can express mass in terms of density? We did that with center of mass. So we're going to see this in a bit, but I'm just foreshadowing it now. This is how you integrate these things. The result of this, though, is people have done this for varieties of objects. So let's just look at one object at a time. A hoop about a cylindrical axis. This is the easiest case. A hoop about a cylindrical axis is the easiest case. Why? You actually can do this integral. I equals the integral of r squared, and we'll use the lowercase r, dm. The axis of rotation here is through the center, so it's kind of like a Saturn's rings kind of situation. All the mass is located at r. All of it's at r. So if r is a constant, what can you do with that? Pull it out. What's the integral of dm? mr squared. This is the worst case scenario. Okay, let me rephrase that. This is the highest moment of inertia you can have for an object, is mr squared. Every other case on here will be a fraction times mr squared. That's going to be the trend. You're going to notice that with every single one of these. So scroll now. Yeah, I'll just look at a different one. If this had some thickness, it's m over 2 r1 squared, that's the inner radius, plus r2 squared, that's the outer radius. Where does this come from? You got a triple integral. I equals the triple integral. And you'd probably use cylindrical coordinates. You'll learn about cylindrical coordinates in Physics 3. And you would integrate, and it'd be a good time. A sphere about the center is 2/5 mr squared. 2/5 is a smaller number than 1. Smaller moment of inertia. Why is it 2/5? Because you got to integrate it. It comes from the integral. Like that is the answer. All right. Now, the last thing I want to point out here is this answer changes if your axis of rotation changes. R is measured from the axis of rotation. So, if you all look at this one in the top left, that's the one that's like Saturn's rings. It's rotating about it. And then you look at this one down here. It's still a hoop, but the answer is different because this one in the bottom right is like a coin spinning. That's the way it's spinning. And because my axis of rotation changed, my moment of inertia changes. So moment of inertia can actually get fairly complex because depending on where your axis is, it's going to change your moment of inertia. So you not only care about the geometry of your object, you care about the geometry with respect to where it's rotating. Okay, so you can see a few cases that we have a solid axis down here in the bottom left. So the solid axis that's rotating kind of like a tube rolling down a hill, that one's 1/2 mr squared. If instead that axis of rotation is happening about, I don't even know what you would describe this. If it's like someone twirling a baton, it's mr squared over 4 plus ml squared over 12, where you actually care about the length of the rod. You didn't care about the length of the rod here because you can see symmetry-wise, it doesn't change how the mass is distributed with respect to the axis. And so, anyway, what I'm conveying here is that where the axis of rotation matters. How your mass is distributed matters. How do you find these? You integrate them on a test. I will give these to you. Okay? I'm not going to give you a sphere and say, in the problem, calculate the moment of inertia and do a triple integral, because the vast majority have not learned triple integrals, so you're spared the suffering. All right. What is really cool, now that we've seen the complexity, now that we've seen all these shapes are different, there's a really, really, really cool rule, and I love it. And it's called the parallel axis theorem, which says if you know the moment of inertia of an object about some axis, if you shift that axis to another axis that's parallel to a parallel axis, look, it's in the name, it's really nice. You take your original moment of inertia and you just add md squared, where d is how much you shifted it. D is just how much you shifted the axis of rotation. And you get the new moment of inertia and done. You don't have to do an integral. This works for any object, no matter how disgusting it is. If you shift the axis of rotation, I don't care how much you shift it. I could have shifted this axis of rotation. It doesn't even have to be touching the object. I could have shifted this axis of rotation let's see. Can I highlight this in a nice way? Sure. I could have moved it all the way off the screen. And as long as I know how far I shifted it, you just add that to it. The axis of rotation does not need to be touching the object. Case in point, the Earth has a moment of inertia about the sun. You can think about the Earth as rotating about the sun, and it has a moment of inertia associated with that. So, this is such a powerful and useful theorem. I really, really wish there was one for if you rotated the angle of the rotation axis, but I haven't found it. But if you just shift it left, right, it's awesome. So good. It makes life so easy. So, let's try it out. A sphere has a moment of inertia of 2/5 mr squared about its center axis. If we instead shift the axis to the side of the sphere, what's the new moment of inertia? Yeah.
If you use a moment of inertia objects, you specify.
Yeah. If I give you all a sphere, I'll tell you in the problem the moment of inertia of a sphere is 2/5 mr squared. You will not need to have these memorized. You do not need to have these on your note card. If you need it for a problem, it will be given in the problem. That's a good question. So, this one, behold, I gave you the moment of inertia of a sphere. I don't expect you to have it memorized or written down anywhere. If I shift the axis of rotation from the center of that sphere to the side of the sphere, what is my new moment of inertia? And I'll even give you the parallel axis theorem. Your new moment of inertia equals the original moment of inertia plus the mass of the object times how much you shifted it. D is the amount you shifted the axis. So that's all you really got to answer in this question. How much did I shift the axis of rotation? That's all you got to answer, and then put that in and do some simple algebra. It's great. No integrals. The red dotted line is my OG axis of rotation. D is how much you shifted it by. How much did I shift it by? All right, we'll go 20 more seconds. And we'll close this out in 5, 4, 3, 2, 1. So again, really the only challenge here, do you know how much it gets shifted? How much does it get shifted? R. It gets shifted by R, the radius of the object. So you just put your original 2/5 mr squared, and you just add mr squared. It's only adding mr squared because I shifted it by R. D equals R. In this specific problem, because that's R. So, anywho, 7/5 mr squared. So I told you all the worst case scenario was mr squared. Clearly we have a worst case, if your axis of rotation is kind of outside the object, that's even harder to rotate. It's harder to rotate a sphere about the side of it than it is the middle of it. Makes sense. Just kind of, you got more mass, you're kind of swinging around. Yeah, and again, you all can experience this. If you all like have a mass really close to your body, it's really easy to like spin in a circle. If you put a mass really far from your body, it's kind of hard to accelerate that. Try it out for yourself. Case in point. All right. So we'll, there you go. Looking decent. Let's do this problem. Let's do it again, but this one's a little bit worse. Using the parallel axis theorem, what is the moment of inertia of a rod of mass m about the axis shown below? The moment of inertia for a thin rod about its center is 1/12 ml squared. So if I was rotating this rod about the center axis, its moment of inertia would be 1/12 ml squared. It comes from integration. We will integrate it probably next class. But what if instead it's at this new location? What's my new moment of inertia? It's the exact same thing you all just did. So try it out. See if y'all can get the answer in terms of the variables given. We're going to do it with parallel axis theorem, and the next class we'll do it with integration. And I'll prove to you why it's so nice to not have to integrate. So, we could, I guess, write our givens. So I naught equals 1/12 ml squared. And then, 2, what are we solving for? We're solving for a new moment of inertia. How do I find the new moment of inertia? Well, thankfully, I remember that the parallel axis theorem exists. So then you just have to ask yourself, how much did I shift the moment? How much did I shift the axis? Again, this is incredibly useful, y'all, because all these objects I'm mentioning, a sphere, a rod, a rectangular plane, almost every object can be kind of represented by a collection of spheres and rods and planes. And so you can find the moment of inertia for each object. You can just add all that together to get the moment of inertia of an entire system. So for example, like an extreme case would be like if I had a ball bearing, if you all had I don't know, it's not ideal, but something like this, it's a bunch of spheres around some cylinders, and you can find the moment of inertia of that whole object, and you can break any complex object into a bunch of simple objects. That's how artists draw pictures. They draw like the face of the sphere and all that stuff. All right. So again, what is the distance that it gets shifted? So really, you got to ask yourself, where did I start? I started at L over 2. And so how much did I shift? I shifted from L over 2 do this, and I got to make certain I don't make a silly mistake here. Here's an easy way to do this. L over 2 instead of 3L over 6. So how much did it shift? 2L over 6. The middle was located halfway. Halfway is 3L over 6. Subtract the L over 6. You get 2L over 6. That's how much it shifted by. So D, how much it gets shifted is 2L over 6. Step 4, just, plug it in. So you get 1/12 ml squared plus m times 2L over 6 squared equals 1/12 ml squared plus 4 over 36. ml squared. Common denominator, you're going to get a 3 over 36, so you get 7. It's great. I say it's great. This is super simple. You know, it's not going to be it's not the worst thing. We're going to integrate next class. So next class, we will do the exact same problem with an integral. And then I'll convince you that these things are wonderful. All right. Last thing I want to point out to you all is a foreshadowing. There's not much more I have to teach you all. Just remind, so rotational kinetic energy is going to be something that exists, but hey, if you're cool with kinetic translational, 1/2 mv squared, 1/2 mv squared, just replace an m with an I and replace a v with omega and you get the rotational one, and it's awesome, and it's great. A rotating object has energy associated with it. We'll see that next class. We'll finish up everything next class. It'll be a good time. We'll be done. Kind of. With content. We'll do review. Yeah. We'll be done with content on Thursday. Tuesday will be review.